Hello everyone, my name is Nga and I am from Ewha Women's University in South Korea. I am very excited to talk about my research that I did in my PhD study, which is tailoring band structure of graphene by impurity effects in the intermediate temperature. As we all know, graphene shows a wide range of device applications, for example, high mobilities, weak spin-orbit couplings, and especially graphene is famous with its unique electronic band structure, which makes it a gapless semi-metal. However, these characteristics also mean that graphene cannot be used in its pure form for nanoelectronics application. Scientists have extensively studied ways to modify graphene, including adding extra spin-orbit coupling through hydrogen atoms functionalization, leading to around 7 milli-electron volt spin-orbit coupling enhancement. Additionally, decorating graphene with heavy metals atoms like cobalt or PB or platinums also introduces additional spin-orbit coupling effects. And they show that the proximity enhanced spin-orbit coupling effect can open a large band gap in graphene. So spin-orbit coupling in graphene and electronic band feature of graphene could be modified by impurity. However, the use of a small number of impurities raises concerns about their stability. Previous studies relied on the photoemission spectroscopy and STM, which are very effective at atomic scale but not practical for large-scale device application. One main goal of these studies was to assess the band engineering of graphene through precise control of atomic defects and structural modulation measured by transport experiments. Weak localization and weak anti-localization effects have been observed in graphene, but only at very low temperature, making experiments challenging. Additionally, the study of graphene-based devices has been primarily restricted to graphene flags, further complicating matters. Consequently, despite being discovered over 2 decades ago, graphene has not found widespread industrial application. Those reasons drive us to make quantum devices beyond wafer scales graphene by introducing disorders or defects. And most importantly, could this device work at intermediate temperature range around 77 Kelvin up to room temperature? In our studies, we aim to investigate the presence of weak localization and weak anti-localization in graphene-based devices and explore the tunability of spin-orbit coupling effects through spin transport. So we utilize a high-quality graphene CVD ground for our experiment. To achieve this, we fabricated various thicknesses of cobalt interlayers layers on top of graphene using a very low deposition rate in the MBE chamber. For transport measurement, we employed an in-situ straddle mask patterning technique to create a 3 nanometer thick platinum hole bar. We prepared in total 8 whole bars, multiple 2 devices at one time. Our expectations were that by using a sufficient thin cobalt interlayers, we could introduce a single atom dopant at atomic level into graphene, thereby adding in a tunabilities of spin-orbit coupling effects. And to explore this, we increased the thickness of cobalt interlayers starting from sample A, which had no cobalt, and to sample B 0.05 nanometers and so on, and the thickest sample is sample E feature a cobalt thickness of 2.5 nanometers. And here are some key results of our studies. At room temperature, all samples showed a positive MR except for sample D and E, which have no MR effect at all. Surprisingly, the sample with 0.05 nanometers cobalt thickness exhibited a higher MR than the sample without cobalt. And at 77 Kelvin, we observe a combination of negative MR and an upturn curve at higher magnetic field, which could attribute to the weak localization and weak anti-localization crossover. We aim to understand the role of the eutathion cobalt interlayers in the influencing to the transport properties of graphene-based devices, and whether it's proof impurity effects at intermediate temperature. To analyze and interpret these observations, we applied a modified XLN model to our experimental data. Sample A and D exhibit a conventional localization effect. In sample B and C, we observe a crossover between weak localization and weak localization effect. Sample B shows a higher elastic scattering rate compared to sample C, suggesting a dominance of intravalley scatterings over electron-to-electron scattering and intervalley scattering. The behavior can be explained by the morphology results. Increasing the cobalt thicknesses up to 0.2 reduces the image brightness. The XRTAM image of sample B, which is 0.05 nanometers of cobalt interlayers, show atomic scale cobalt particles uniformly distributed in the multilayer growth graphene without clusterings or isolated islands. Cobalt likely diffuses into the graphene layers without forming chemical bondings with the carbon atoms. And this demonstrates successfully atomic impurity separation in wafer scale graphene. In summary, our findings suggest that different MR responses in graphene-based devices are influenced by disorder and the morphologies of cobalt interlayers. This leads to a weak localization and weak anti-localization crossover and the potentials of a proximity effect. The interplay of intrinsic spin-up coupling, Raspa-like spin-up coupling, and exchange coupling in our graphene hybrid systems explain this observation. These findings provide insights into the role of disorders, morphologies, and spin-up coupling effects in graphene-based devices. Thank you very much for listening to my talk until now. If you are interested in my work, please come to see my poster. Thanks again.